explain what is meant by tunneling, right? Okay, so as a alpha particle approaches a nucleus, right? Remember that this is positively charged. This is positively charged. These guys repel each other, right? So this guy goes, and it's repelled. Whoa, goes back out, right? It's like two magnets, like two North Pole magnets coming in toward each other, right? Okay, so we can do the calculation. Do we understand what's really going on here? I don't know. I'm not sure. Okay, so this guy's being repelled by this, right? And the potential energy of that alpha particle is given by K Q1 Q2 over R, right? And if we draw that curve, where this is distance, right, in meters, and then this is the potential energy, okay? That curve just does this, okay? Until you reach the radius of the atom, or the nucleus, sorry. When you reach the nucleus of the radius of the nucleus, the alpha particle literally can then exert a strong nuclear force and vice versa on each other, right? And suddenly it's attracted to it. So when it reaches that radius there, okay, it's pulled in, and the alpha particle is going to exist at some level here, right? There's levels inside this nucleus, right? I know nothing really about them, but I know there are different levels, right? So let's imagine that the alpha particle, when it's sucked in, exists at some level like this, right? Okay. Now, what's interesting is that, of course, when the alpha particle escapes, I haven't drawn this very well to scale. It's much, much higher, and this is much, much lower. But when it escapes, we see it with this much energy, right? And this is the alpha particle energy that we calculate there. That's the energy we see because that's the energy it has long term. It's got this much energy, right? Okay, you can see how far out of scale this is, right? 6.5 MeV, right? But to escape, right, to get the alpha particle back in, you've got to actually get over the top of this thing, right? And this thing is 35.5 MeV. We just figured that out, right? That's this guy, right? Okay, so to get that close, we need that much energy. To get out, though, somehow it has this energy, right? So that was, a great puzzle for them, right? And so, what they would say is, well, how does it get out? Well, it tunnels through this barrier here, right? Okay. But really what's going on here is that and you can look at it two different ways, right? One is that either the position is uncertain, right? Right? You can say, well, then the alpha particle's like here, and it's like, damn, I'm gone, baby, Because if it's here, suddenly the Coulombic force is acting on it, and maybe it's gone, right? Or you can say, look, the energy of this thing can be uncertain, right? And this is, of course, the calculation we make because we know these energy differences, right? I mean, we could do this too, right? We know these energy differences, and the energy difference is the calculation that we did right here. Okay. And so really what it is that the alpha particle, by random chance, either briefly borrows the energy to escape this well that it's in, or its position is uncertain and it's outside and maybe it's gone. Okay. So anyway, we're trying to explain the discrepancy between the energy needed to put the alpha particle in and the energy it has when it eventually escapes through alpha decay. All right.